Do you remember the car scenario from the first of the semester? You're in a car on a straight flat road. From rest, you accelerate from 0 to 55 miles per hour in 10 seconds. From that time on, you maintain a constant speed of 55 miles per hour. Well, I gave you this position function, and we use that to find the speedometer reading at any time t. Remember, I told you that at the end of the semester, you would know enough calculus to be able to come up with this position function on your own. And we're now to that point. Let's figure out how to come up with this position function on our own. First of all, we know the velocity at time t is, or the velocity at 10 seconds and after 10 seconds is 55 miles per hour. Now, I realize that I'm doing this in miles per hour. We'll have to, at the end, convert to feet per second to get these numbers up here in this position function, as was originally stated. So what's the position for t is greater than or equal to 10? The velocity is positive 55 because I'm going in the positive direction. Well, I know that s prime of t, the derivative of position, is velocity. So I had to take the derivative of some function to get 55. What did I take the derivative of to get 55? Think about that. What do you take the derivative of to get 55? Wouldn't it be 55t? What's the derivative of 55t? 55. So I'm going backwards on derivatives. I've now given a derivative, and I'm trying to find the original function. I'm given velocity, and I'm trying to find position. But wait a minute. What if I had some constant here? What if I had 55t plus 2? Isn't its derivative 55 also? What if I had 55t minus 7? Isn't its derivative 55 also? So there's an arbitrary constant here. If I take the derivative of s of t equal 55t plus c, and it makes sense to do that when t is greater than or equal to 10, guess what? I get 55, and that's 55 miles an hour. We still have to find this constant c. The way we'll do that is the position at t equal 10 using this first piece, and the position at t equal 10 using this piece will have to be the same. The function's continuous, in other words. So we'll use that piece of information to find this arbitrary constant c. We'll keep on doing more parts of this problem, but at the end of the semester we'll be able to come up with it exactly. But today, and really for the next week, we're going to be going backwards on derivatives. We're given the derivative. We want to find the original function. That's called anti-differentiation. Sometimes it's called indefinite integration. And we're going to introduce this symbol. This symbol. This is a symbol altogether for the most general antiderivative. So the way that we're going to write this original problem we did is we wanted to find the antiderivative of 55. This expression right here says, find the most general antiderivative of 55. What was our answer? It was 55t plus a constant. This symbol, this dt, is a part of this symbol. Looks like a kind of a strange choice of symbol, but again, by the end of the semester, you'll see why we chose that. That means look in here. Look at what's here. In other words, look at the 55. Find a function that you can anti-differentiate to get 55. So that's 55t. But we've got to give the most general antiderivative. We've got to have this constant here, because there are infinitely many functions that you can differentiate to get 55t. They all differ by a constant. This is called the indefinite integral of 55. Indefinite integration is just another name for anti-differentiation.